Monday night, the sky over Buenos Aires turned green. A fireball, electric, fast, and violent, tore across one of the most populated cities in the Western Hemisphere at 40,000 kilometers per hour. Security cameras caught it from every angle. Meteorological sensors logged the speed. And then, before anyone had finished asking, "What was that?" the sky did it again. 48 hours later, British Columbia, Canada. Over 100 reports filed before most people had their morning coffee. Then, a third signal. Hawaii. Same window. Same eerie emerald glow. Same unanswered silence from the databases that are supposed to track exactly this. 3 continents, 72 hours, one impossible pattern. But the problem isn't just the fireballs. The problem is the math. According to the only peer-reviewed model we have, this debris stream was supposed to have vanished into the dark by April 7th. The window was officially closed. The science said, "Stop! The solar system clearly didn't get the memo. We are told that our skies are monitored, that our infrastructure is safe." But as these green streaks continue to punch through our atmosphere weeks past their expiration date, we have to ask, are these just lingering echoes? Or is Earth flying into a region of space we haven't even mapped yet? Stay with me, because if this pattern holds, the real danger isn't what's passing through the sky. It's what we've been missing right in front of us. Now, let us get into it. To understand the true scale of this anomaly, we must move past the spectacle and look at the geometry of the arrival. In the world of investigative meteorology, a single fireball is a curiosity. A cluster is a warning. But a global distribution across 3 continents in under 72 hours? That is a signature of something systemic. Let us start with the raw data, beginning where the darkness first broke. April 27, 10:51 de la tarde local time, Buenos Aires, Argentina. A metropolitan area home to 13 million people was suddenly bathed in a violent, electric emerald glow. This wasn't the soft, flickering light of a typical meteor. Security cameras and dashcam footage captured a high-velocity bolide punching through the atmosphere at 40,000 kilometers per hour. Scientists noted a distinct plasma cap, a superheated bubble of ionized gas surrounding the leading edge of the object. This feature only occurs when a body is dense enough to maintain its structural integrity against the brutal friction of the lower atmosphere. It didn't just graze the sky, it penetrated it. While the South American reports were still being scrubbed from social media, the sky spoke again. Dawn, April 29th. British Columbia, Canada. Less than 36 hours after the Buenos Aires event, a second fireball, identical in its characteristic green spectral signature, streaked across the Canadian horizon. Unlike the event in the south, which sat in a data vacuum, this bolide was captured by one of the most robust reporting infrastructures on Earth. Over 100 independent reports were filed with the American Meteor Society before the sun had even risen. Witnesses described a fast-moving emerald spear that left a persistent vapor trail hanging in the upper atmosphere for several minutes. And then, the third signal, April 29th, Hawaii, USA. In the same narrow 72-hour window, a green light crossed the sky over Kona. This event remains the most controversial of the cluster. While social media footage shows a spectral match to the previous 2 bolides, official databases remained silent. Was it a natural meteoroid? A re-entering piece of satellite debris? Or something else entirely? Look at the math of this distribution. Buenos Aires sits at 60 degrees west. British Columbia is at 125 degrees west. Hawaii is at 155 degrees west. In 3 days, these events were distributed across nearly 200 degrees of longitude. That represents more than half the Earth's circumference. These objects did not come from a single localized point in the sky. They were not confined to one hemisphere. They were arriving from different trajectories, yet they shared the same chemical signature and the same impossible timing. At first, the scientific community tried to frame this as a coincidence, a statistical quirk of a busy spring. But as we began to cross-reference these events with the established orbital models, the coincidence theory fell apart. Because according to the maps we've been using to navigate the solar system, the sector of space we were occupying on April 27th was supposed to be empty. The timeline was out of sync, the geography was too wide, and the model was about to be proven wrong. Human beings possess a deep, primal hunger for certainty. When the sky begins to behave in ways that defy our memories, we look to the men and women with the instruments and the equations to tell us that we are safe. In the chaotic weeks of March 2026, as green fireballs rattled windows across the globe, that certainty arrived in the form of a single, rigorously peer-reviewed document. It was more than just a paper, it was a map. It provided the first real explanation for the electric green surge. The model was spearheaded by a researcher named Patrick M. Schober. Using a massive dataset of 282 coordinated meteor detections from global monitoring networks like Desert Fireball and the Global Meteor Network, Schober did what felt impossible. He identified a specific, newly characterized debris stream. He gave the ghost a name, M2026A1. The origin of this debris wasn't a traditional icy comet, but something far more interesting to the scientific community, a rock comet. Unlike the dirty snowballs we are used to, rock comets are primarily rocky asteroids that occupy orbits, taking them dangerously close to the Sunday. Schober's model proposed a fascinating physical mechanism, sodium-driven fragmentation. As this parent body reached its closest point to our star, the intense solar heating began to vaporize the sodium trapped within its rocky crust. This internal pressure caused the asteroid to fracture, shedding magnesium-rich stones and dust along its orbital path like a trail of breadcrumbs in the void. This explained everything. The electric green glow? That was the spectral signature of ionized magnesium and sodium burning up as those dense rocks hit our atmosphere. The unusual brightness? It was the result of a fresh, unweathered debris stream. For a moment, the world felt a sense of profound relief. The mystery was solved. We had moved from a state of fear into a state of false security. The hallmark of high-level science is precision. The Schober model didn't just tell us what was happening, it told us exactly when it would end. Based on the orbital intersection of Earth and the M2026A1 debris field, the model established a definitive, active window. The encounter was set to begin on March 16th and reach its absolute geometric conclusion on the 7th of April 2026. Throughout late March, the data was a perfect match. We saw 12 major fireball events, a factor of 6 increase over the baseline. But because the model predicted them, they didn't feel like a threat. They felt like a validation of human intelligence. We sat in our homes, watching the news, and believed the experts when they said the door would close on April 7th. We were told the debris field was finite, the geometry was understood, and the solar system was once again predictable. On April 7th, the scientific community symbolically closed the book on M2026A1. The stream had passed. The threat was over. For 20 days, the world went back to sleep, confident that the anomalous spring was behind us. But while we were looking at our models, the sky was preparing to prove them wrong. The Buenos Aires bolide didn't care about the April 7th deadline. The British Columbia event didn't care about the peer-reviewed math. They arrived in a sector of space that was supposed to be clear. They arrived in a window that officially didn't exist. Everything was understood. Right up until the moment reality decided to stop following the map. And what we are finding now, in the silence of these late April nights, is that the model didn't just fail a deadline. It missed the true nature of what we are flying through. In the precise language of celestial mechanics, a deadline is not a suggestion. It is a mathematical boundary, a wall built by the laws of physics. When a model as rigorous as M2026A1 defines an active window, It is calculating the exact intersection of Earth's velocity and the geometric boundaries of a debris trail left by a rock comet. According to that model, on the 7th of April, 2026, Earth reached the edge of the debris field. By every law of orbital dynamics we've mastered, the encounter was over. The sky should have gone quiet. The anomalous surge should have faded into a memory. But as we sit here today, on April 30th, the data has effectively shredded that map. The Buenos Aires bolide occurred on April 27th. That is 20 days past the threshold. In the scale of the solar system, 20 days is not a lingering tail or a statistical margin of error. In those 20 days, Earth traveled approximately 51.8 million kilometers along its orbit. To suggest that we are still seeing residual fragments from the M2026A1 stream is like suggesting a car could be hit by a localized rainstorm 50 miles after it drove into a bone-dry desert. The geometry simply does not support the theory. In the precise language of celestial mechanics, a deadline is not a suggestion. It is a mathematical boundary, a wall built by the laws of physics. When a model as rigorous as M2026A1 defines an active window, it is calculating the exact intersection of Earth's velocity and the geometric boundaries of a debris trail left by a rock comet. According to that model, on the 7th of April, 2026, Earth reached the edge of the debris field. By every law of orbital dynamics we've mastered, the encounter was over. The sky should have gone quiet. The anomalous surge should have faded into a memory. But as we sit here today, on April 30th, the data has effectively shredded that map. The Buenos Aires bolide occurred on April 27th. That is 20 days past the threshold. In the scale of the solar system, 20 days is not a lingering tail or a statistical margin of error. In those 20 days, Earth traveled approximately 51.8 million kilometers along its orbit. To suggest that we are still seeing residual fragments from the M2026A1 stream is like suggesting a car could be hit by a localized rainstorm 50 miles after it drove into a bone-dry desert. The geometry simply does not support the theory. We relied on the Schober model because it gave us the comfort of an end date. It allowed us to believe that the anomalous spring had a defined exit strategy. But by occurring 20 days late, these late April fireballs have proven that the exit was an illusion. We have entered a sector of space that our models marked as clear. We believed we were flying through a narrow stream. The data is now suggesting we have flown into a debris region, a vast, unmapped zone of the solar system saturated with dense metallic objects that our survey telescopes systematically failed to identify. The map didn't just have an error in the dates. The map was drawn for a different solar system than the one we are currently traversing. And as we look closer at the data mismatch in these final days of April, the numbers are starting to show that the surge didn't just survive the deadline. It is actually intensifying. The window didn't close. We just moved deeper into the storm. And what the data shows next is even more concerning. Numbers are the heartbeat of investigative meteorology. They don't lie, and they don't have a bias. To truly grasp the severity of the situation we are navigating, we have to look at the baseline. Historically, the American Meteor Society logs an average of 2 significant fireball events per month. Events large enough to generate more than 100 witness reports. March 2026 didn't just exceed that baseline, it shattered it. 12 major events in a single month. That is a factor of 6 increase. When Mike Hankey, one of the most methodologically rigorous analysts in the field, processed these numbers, he characterized the deviation as a 4.5 sigma anomaly. In the world of high-level statistics, 4.5 sigma is not a lucky streak. It is a mathematical neon sign telling us that the fundamental rules of the environment have changed. It is a level of rarity that, in any other field, would trigger an immediate global emergency. But it is the physical character of these events, not just their frequency, that should keep you awake. The sonic boom rate for the March and April events is sitting at a staggering 79%. Think about what that means. Most meteors are fragile, loosely bound aggregates of ice and dust that disintegrate in the thin upper atmosphere. They leave a pretty light, but they don't leave a sound. A sonic boom is proof of structural integrity. It is the calling card of a different animal entirely. It means these objects are dense enough, heavy enough, and structurally coherent enough to survive the initial atmospheric shock and penetrate deep into the dense air where we live. These are not space dust. These are rocks, and they are hitting us with a frequency we haven't seen in the observational record. When Earth crosses a standard debris stream, we see a decay curve, a sharp spike that fades predictably as we leave the material behind. But April 2026 is showing us a plateau. Despite the M2026A1 window closing on April 7th, the activity has not decayed. April is currently tracking at 2.5 times the historical baseline. And remember, this 2.5 figure is the floor. It counts only the events that made it into the official databases. It does not count the Buenos Aires bolide, which we've already established had millions of witnesses but 0 official entries. It does not count the events over the 71% of our planet covered by ocean. If the frequency isn't dropping, it tells a chilling physical story. Earth is not moving away from a storm. We are moving through a region. A plateau is what happens when the debris density ahead of you is identical to the density behind you. It suggests that the M2026A1 model correctly identified one localized vein of material, but was completely blind to the massive cloud surrounding it. We are navigating a sector of the solar system that is far more saturated with dense, metallic objects than any of our maps anticipated. The Schober model gave us a window of 3 weeks. Reality is showing us that the window may stay open for months. We are told that our skies are understood. We are told the anomalies are explained. But as the April plateau sustains itself, we are forced to confront an uncomfortable truth. We are counting the raindrops we can see while having no instruments to measure the size of the storm we are actually inside. And the reason we are so blind? It lies in the gaps of the very systems we trust to keep us safe. When a fireball as massive as the Buenos Aires bolide lights up a sky shared by 13 million people, we instinctively assume it is being etched into the permanent scientific record in real time. We trust that our planetary guard is watching, logging, and analyzing every intruder. But as of this recording, if you search the American Meteor Society's primary database for the night of April 27th, you will find a number that should disturb you. 0. Not a handful of reports. Not a pending investigation. 0. How does a brilliant, magnesium-rich object, witnessed by millions and captured on dozens of high-definition security cameras, simply fail to exist in the world's most cited fireball database? The answer isn't a shadowy conspiracy. It is a structural failure of our civilization's observation architecture. The AMS is a masterpiece of public outreach, but it is optimized for a specific geographic and linguistic slice of the world: North America and Western Europe. This is the birth of what we call dark data. These are atmospheric events that are physically real, tracked by local weather sensors, and shared by millions on Spanish-language networks, but they never cross the language barrier into the systems we rely on to understand near-Earth space. For the official global record, if no one logs it in English on the right platform, the event effectively never happened. This creates a dangerous funhouse mirror effect. We believe we are seeing a 2.5 times surge because that is what our monitored zones tell us. But when we realize that a city lighting event in the southern hemisphere can go completely uncounted, we begin to understand that 2.5 is not the ceiling, it is the floor. The true global anomaly is almost certainly far more intense than the official numbers dare to suggest. The Buenos Aires paradox is merely a symptom of a much larger global ailment. To understand why our models are failing to predict this late April surge, we have to acknowledge the brutal math of our planet's surface. 71% of Earth is covered by ocean. These are vast, sensing vacuums where bolides can explode with the force of tactical weapons and leave no trace. No witnesses, no reports, no data. But the blind spots aren't just on the ground. They are built into the orbital geometry of our detection systems. Consider the solar approach, the direction of the Sunday. Our ground-based optical telescopes are essentially blind to any object approaching us from the glare of our star. This is exactly how the 20-meter Chelyabinsk meteor sneaked past every global detection network in 2013. You cannot point a camera into a spotlight and expect to see a pebble. Today, as we fly through this unmapped debris region, we are essentially looking at the universe through a narrow, dusty slit, while convinced we have a panoramic view. Even our most prestigious systems, like NASA's CNEOS, carry documented accuracy gaps for smaller events. For the sub-kiloton bolides we are currently tracking, location errors in the database have been recorded at over 1,800 kilometers. Let that sink in. A system with continental scale uncertainty is what we are using to map a 4.5 sigma anomaly. We have built an architecture for a quiet version of the solar system, one where we only worry about the giants. But April is proving that we are now moving through a swarm of smaller, dense objects, a population that exists in the gaps of our instruments, in the darkness of our oceans, and in the silence of our reporting systems. We didn't see the plateau coming because we weren't designed to see it. And as we're about to find out, one of these unseen objects just came much closer to our infrastructure than anyone was willing to admit. The silence of our oceans and the linguistic gaps in our reporting systems are only half the story. To truly understand the unseen surge of April 2026, we have to look into the light. There is a specific direction in the sky that acts as a permanent, impenetrable cloak for incoming objects: the Sunday. In the world of planetary defense, this is known as the solar approach. Most of our sophisticated survey telescopes are ground-based optical systems. They are designed to scan the dark, star-filled quadrants of the midnight sky, but they have a fatal structural flaw. They cannot look into the glare. This is exactly how the 20-meter Chelyabinsk meteor, Lern, sneaked past every detection network on Earth in 2013. It didn't hide in the darkness, it hid in the light. As we fly through this current debris region, we are essentially navigating a shooting gallery while staring directly into a spotlight. Any object approaching us from a low solar angle is effectively non-existent to our sensors until the moment it hits the atmosphere. We aren't just missing data from the southern hemisphere or the Pacific Ocean. We are missing an entire hemisphere of the sky. Even when we are looking in the right direction, we are often using the wrong eyes. Most small asteroids, the kind currently saturating our atmosphere, have an albedo, or reflectivity, roughly equivalent to a piece of coal. They don't reflect sunlight, they absorb it. They are dark travelers in a dark void. To see them before they arrive, we need infrared, IR space-based telescopes that sense the faint thermal signature, the heat of the rock against the cold background of space. But here is the existential reality. As of late April 2026, our infrared surveillance of near-Earth space is still in its infancy. Projects meant to close this gap have faced years of budget shifts and launch delays. We are trying to track a 4.5 sigma anomaly using 20th century optical technology, while the objects themselves are playing by the rules of 21st century physics. This creates a profound geographic asymmetry. Our understanding of the normal state of the sky is based almost entirely on what we can see from the northern hemisphere's land masses. We have built a global baseline using only 30% of the globe's surface. When we say the fireball frequency in April is 2.5 times higher than normal, We are making that claim based on a tiny biased sample of the atmosphere. If we could somehow illuminate the dark zones, if we had sensors over the Antarctic, the deep Amazon, and the southern reaches of the Indian Ocean, that 2.5 multiplier would likely skyrocket. The real problem isn't what we don't understand about these magnesium-rich fireballs. It's that we have reached the limit of our capacity to even observe the environment we are in. We are measuring the raindrops that hit our window, while the storm itself remains unmapped. We aren't just passing through a debris stream. We are traversing a sector of space where our primary detection systems have a known structural blind spot. And as the late April plateau continues to defy every model, we have to confront the most unsettling realization of all. The real surge isn't what's lighting up the sky. It's everything else that is still out there, moving silently in the gaps between our instruments. And one of those silent objects just proved how thin our protection really is. To truly understand the stakes of the current anomaly, we have to look at the event that didn't make the headlines. While the world was distracted by the spectacular green lights over Buenos Aires and Canada, a near-Earth object ghosted our planet in a way that should change how you view the sky. It was an asteroid, approximately 5 meters in diameter. In the vast scale of the cosmos, 5 meters is a grain of sand. But in the scale of human survival, it is a boulder traveling at ballistic speeds. This object didn't just pass near us. It slipped beneath the geostationary ring, the high-altitude orbit where our most vital telecommunications, weather, and GPS satellites reside. It was closer to us than the very systems that power your modern life. And here is the fact that should stop you cold. There was zero public warning issued. Our detection networks didn't identify it until it had already passed. Now, consider the context. 5 meters is exactly the size class of the bolides we have been tracking throughout this late April surge. If the entry angle had been just a few degrees lower, this asteroid wouldn't have been a near miss. It would have been another green explosion over a populated city, likely rattling windows and triggering seismic sensors across 1,000 square miles. Our current planetary defense architecture is excellent at tracking the planet killers, the giants over a kilometer wide. We have mapped them. We know where they are. But the small ones, the 5 to 20 meter rocks that can shatter glass and injure thousands, remain effectively invisible to us. They exist in a structural blind spot of our technology. We almost didn't see it because we weren't looking for it. And if we are indeed flying through a region of space more crowded with these objects than our maps predicted, then the near misses are happening much more frequently than the official records will ever show. We are, quite literally, navigating a shooting gallery with our eyes closed. This near miss is the bridge between the fireball story and the reality of our situation. It proves that the 5 times baseline we are seeing in April isn't just a collection of pretty lights. It is a signal of a much denser population of objects currently occupying Earth's immediate neighborhood. The detection floor, the minimum size an object must be for us to see it in advance, is currently set at a level that misses nearly everything we've seen in the last 72 hours. We are detecting the impacts, but we are missing the arrivals. This creates a terrifying epistemic gap. We can study the storm by where the raindrops fall, but we have no instruments to look at the clouds themselves. The 5-meter asteroid that buzzed our satellite ring without warning is the definitive proof of that gap. It is a reminder that the window of March and April 2026 isn't just about what we understood, it's about everything we failed to see. The model closed on April 7th. The fireballs didn't. And the near misses, they are only just beginning to tell us the truth about where Earth is actually going. The question is no longer, when does this end? The question is, what are we actually flying through? And as the theories collide, the answer may be much larger than anyone was willing to admit. This brings us to what we call a theory collision. The data has officially outpaced the M2026A1 model, and the scientific community is now forced to reconstruct the reality of the territory we currently occupy. We are no longer debating if the model failed, but why. There are three primary investigative paths emerging from the specialized research circles, and each one tells a very different story about our future. The first path is the peripheral fringe hypothesis. This is the most conservative view. It suggests that the M2026A1 stream is simply much larger and more diffuse than Patrick Schober's initial model could constrain. In this scenario, the core of the debris passed Earth in March, but we are now traversing an outer fringe, a massive tail of material that has drifted millions of kilometers away from the main orbital track due to solar radiation pressure over centuries. It's the same rainstorm, just much, much wider. The strength of this theory is its parsimony. It doesn't require a new source, but its weakness is the geography. If these were just leftovers, they should still share a localized radiant. As we've seen, the late April fireballs are coming from everywhere. The second path explores overlapping swarms. This is the crossing streams hypothesis. It proposes that while M2026A1 explained the March peak, a second, completely unmapped debris system has intersected Earth's path in late April. This would explain why the frequency didn't decay. As one source faded, another ramped up. These could be fragments from a different parent body, another rock comet, or an asteroid family with orbital resonances that bring their debris to our doorstep at exactly this time of year. This theory naturally explains the broader radiant distribution we are seeing. Multiple sources produce multiple directions, but it carries a chilling implication. It suggests that our near-Earth environment is far more crowded with uncharacterized debris than we ever admitted. It means there are ghost streams out there that we only discover when we are already inside them. The third path, and perhaps the most haunting, is the systemic shift. This theory moves away from the idea of streams entirely. It suggests that the background density of small bodies in our sector of the solar system has genuinely increased, whether due to a recent collisional breakup in the asteroid belt or a gravitational resonance shift. We may be entering a debris region, a permanent cloudy zone of space that our historical baselines never accounted for. Under this theory, the March surge wasn't a temporary spike, it was an entry point. The late April plateau is not the end of a cycle, but the beginning of a new, higher normal. It suggests that Earth is not just passing through a trail of dust, but has moved into a more dangerous neighborhood of the cosmos. It aligns with the anthelian doubling we saw in Q1, a signal that the entire background environment is shifting. This is the collision. Three theories, each attempting to explain why the fireballs are still here 20 days past their deadline. The conservative model is broken, the overlapping model is unproven, and the systemic model is terrifying. I will not tell you which one to believe, but we must acknowledge that the single stream comfort of March is gone. We are traversing a region of space that is actively testing the limits of our capacity to see and understand. And as Earth continues its journey deeper into this unmapped zone, we are realizing that the real challenge isn't the rocks we can count, it's the environment we've failed to map. The question is no longer, when does this end? The question is, what else is waiting for us in the dark? And the answer may lie in a perspective we've been too afraid to consider. We have spent this entire investigation searching for a timeline, a beginning, and an end to the electric green anomaly. We looked to the peer-reviewed models. We tracked the 1,693 long-duration events of March, and we waited for the predicted decay of the April 7th window. But as we reach the final hours of this month, we have to confront a reality that no database was designed to record. The Buenos Aires bolide, the Canadian spear, and the Hawaiian signal were not just late arrivals. They are the evidence of a fundamental shift in our planetary environment. We have traveled over 51 million kilometers since the Schober model officially closed its window. In that distance, the frequency of massive, structurally robust objects entering our atmosphere has remained at 2.5 times the historical baseline. The plateau of chaos has not broken. We have also uncovered the gaps. We now know that our planetary guard is linguistically and geographically biased, that a city lighting event over Buenos Aires can exist for millions of people, and yet be dark data for the scientific record. We know that 71% of our planet is an unmonitored vacuum, and that our current detection floor allows boulders the size of houses to slip beneath our satellite rings without a single whisper of warning. But the final realization is much deeper than a failure of sensors or a mismatch in models. Throughout human history, we have viewed space as a vast, empty void where things occasionally come to hit us. We treat ourselves as a stationary target, and the universe as a source of random, incoming threats. But the data of 2026 suggests we need to flip that perspective entirely. What if these objects aren't passing through Earth's neighborhood? What if Earth is passing through them? What if we have entered a sector of the solar system that is simply different? A region shaped by an ancient collisional cascade or a gravitational resonance shift that we never mapped because it was populated by dark, magnesium-rich objects that exist below our detection floor. If this is true, we are no longer waiting for a shower to end. We are navigating a new, more crowded territory. We are moving into a new normal for near-Earth space. Our technology is modern, our satellites are precise, and our models are elegant. But before the sheer, unrelenting scale of the unseen surge, we are reminded of a very old truth. Human infrastructure is fragile, and our understanding is limited by the very tools we use to see. The green fireballs didn't stop on April 7th. They didn't stop because the environment ahead of us is just as saturated as the environment behind us. We are travelers in a changing cosmos, and we have only just begun to realize that our maps are out of date. I want to hear from you. We need every set of eyes on this. Where were you on the night of April 27th? What is the weather doing in your corner of the world? Drop your location and any unusual sightings in the comments below. We are building our own database now, one that doesn't care about language barriers or geographic blind spots. Because if Earth has indeed entered a new region of space, then the question isn't, what is coming next? The question is, how long have we already been inside it? Stay vigilant. The data is still coming in, and we will be here to connect the dots.